All right. So today we'll be covering transient problems as they apply to solid mechanics. In the previous lecture, I covered transient problems as they apply to heat transfer, or even more generally speaking, problems where you could have transient events such as moisture diffusion, heat transfer. And today I'll be applying the concepts to a solid mechanics. Okay, solid mechanics. So we've covered already what the strong form looks like for an elastic bar. Previously, I did not show you this term. Okay, this term was 0. There was no acceleration. Today, we'll be adding that term. Okay, and that's basically mass times acceleration for the elastic bar. And so the process to develop the finite element formulation for elastic bar is no different from heat transfer. Very similar approach. I think, in fact, I may be tiring you over and over by showing you the governing equation, and then I'll form the strong form, I'll form the residual function, I'll get the weighted residual, I'll integrate by parts. I think by the end of this class, I think you will sleep thinking about this, okay? But we took this, we formed the residual error, so I put this to the left-hand side, and you can see here, I've actually brought this two terms to the right-hand side, is what I did. And then multiply by this weight function v, and that's my weighted residual right there. So I made the residual function orthogonal to the space of weight functions. And then I've integrated over the domain. Okay. The next step is we've integrated by parts to form the weak form. And you guys are all familiar with that. So here, I'm not going to integrate by parts the time derivative, not that one, because we're not discretizing using finite elements the time domain, just a spatial domain. So because we're only integrating by parts, we're only discretizing the spatial domain, which is only this one here. Then for that reason, we'll be integrating by parts just that term. And so what I've done that without showing you the steps, because I think everybody here knows how to do that. So I jump straight to the weak form here. So that goes inside the integral, and that term actually generated the boundary conditions of the problem. Okay. Any questions on this? Any questions on this? Everybody's familiar on how to develop the weak form. No different from what you've seen before, but now we have a mass acceleration term, but we're not really touching that much. We're just multiplying that by v, leaving that alone. Okay? Any questions? We're good? All right, so now that I have the weak form, this is the weak form of the problem. It's not the weak form of Euler-Bernoulli. At this point in time, this is the weak form of the problem. And what I want you to notice is that I could have loads applied at either end. They're a function of time. And then I'll have also distributed forces, potentially. I could have a problem like that, where the distributed forces are changing as a function of time. And then finally, I have the mass, and then I have the spatial domain, the part that has to do with the spatial domain. Okay? And this term is also related to the strain energy of the bar. Okay? And that's related to the potential energy of the bar. So are this. Okay. Any questions? So the weak form of Euler-Bernoulli now will be applied. Now we can do that. So for the weak form of Euler-Bernoulli, we'll develop the element formulation. And I'm going to take an example of a linear element. So for the linear element, everybody knows that for a linear element, I have what? How many unknowns? 2 unknowns. So then I should have how many shape functions? 2 shape functions, very good. And so now I have taken my approximation function, which is also a function of time. I'm missing a comma t there. And I'm making use of separation variables. So now my nodes are a function of time, and my shape functions are a function of x only. Okay. So this becomes n times u. Okay. Each of the shape functions are given there. That's for a linear element. And you can see that this works out. If I substitute it here xi, okay, what happens? I get 1 there. So I get 1 there, and I get 0 at the other node, so Kronecker delta property. And then if I substitute xi here, I get 0 at that node, but xj gives me 1 at this node. So I'm getting exactly what I should get at each node, ui and uj, okay, as a function of time. And again, we went from weak form Galerkin, the exam I just returned to you. We went from unknown coefficients that had no physical meaning, like in that exam, and then we taken that and we brought some physical meaning to them. These are the unknown coefficients now, okay? These have meaning now, and I can connect them from element to element now in a more straightforward manner, which I could not do very well with the regular weak form Galerkin formulation that we went through before. Then I can also look at a quadratic element as an example. A quadratic element will have 3 nodal unknowns. Okay, so I'll have 3 shape functions. And these shape functions, I'll put them in a matrix called n bold. And then these unknown quantities, 1 at either extreme and 1 in the middle, uk, will go in the middle, somewhere in the middle. Doesn't have to be right in the middle, can be somewhere in the middle. And these are the shape functions, which everybody here is familiar on how to get them. You should be very familiar on how to get them without going through the math. We talked about how to do that in a few lectures ago. Okay, so now my unknown coefficients are ui, uj, and uk as a function of time. Okay, any questions so far? So we came up with approximation functions. Okay, this is more systematic than what you saw in the first 3 or 4 lectures where there is no systematic approach. But this approach gives you a very clear definition of how your approximation function looks like for linear element and quadratic element. Okay, so now I'll go ahead and I will notice here that I'll have to calculate derivatives, okay, of u, of v. I'll have to calculate derivatives of u here with respect to time. So I'll start. U is a function of x comma t. And this is my approximation function, don't you agree? Because these are the shape functions. And so these are the nodal unknowns. You agree that that's my approximation function? So I'll start with that. I also realize I have to take the derivative of u with respect to x. So that's that. And so the only thing as a function of x is n. So n bold with respect to x. And then times u. Okay, just that. And so this becomes b bold right here. And that's u bold. I'm doing a little different from what I did in the previous lecture, just to give you a different perspective. But the same answers will be provided at the very end. So derivative of u with respect to time, 2 derivatives. This is not a function of time, so this becomes a second derivative of u instead. So I have n bold u double dot. Okay, everybody agrees with this. No questions so far. Excellent. So then for v, I'll substitute n transpose, and I've shown you many times why that is the case. I also have to calculate the derivative of v with respect to x. So for that reason, I'll calculate right there derivative of n transpose with respect to x gives me b transpose. So anytime I see derivative of v with respect to x, I'll make it b transpose. Anytime I see v, I'll make it n transpose. Okay? Yes? It's getting repetitive. But that repetition is what makes you a champion. Okay? All right. So for that, I have n u double dot. So that's what you see there. Okay? For v, I'll make it n transpose. For derivative of u with respect to x, I have b u. And then for v, derivative of v with respect to x, I have b transpose. Okay? Then I have q times v. V is n transpose. And I have my matrix of forces, vector of forces, q bold. Okay? And you can verify at home that this will go away. It will be either 1 or 0. These weight functions will become 1 or 0 because I'm choosing them as the shape functions, remember. We're choosing the weight functions to be the basis functions. And so in this case, the weight functions are the shape functions. And you will use Kronecker delta property to arrive to the q bold here. Okay? All right, that is my element formulation. I just did it in a couple of steps. Okay? And I hope you're practicing at home for your homework that's due this Thursday. I'm making you do this twice, problem 1 and problem 2. Okay? So let's practice that. The only difference is that you probably don't have this term. Okay? And the second difference is that's Timoshenko and Euler-Bernoulli. Of course, they're different from this. But the process is the same. The process is the same. Okay, I have the element formulation. I can expand it nicely now. So I can realize this is not a function. Sorry, u double dot is not a function of x. U is not a function of x. Basically, I can put the u double dot outside of the dx integral. And I can put the u bold outside of the integral, not a function of x. And then I have my forces, my distributed forces, and the q bold, the vector of internal forces to the element. Okay. Now I quickly recognize this as my mass. This is my mass right there. That is the stiffness matrix. So that's m u double dot k u equals the forces, distributed forces, plus the internal forces. Any questions on that? Fairly straightforward, don't you agree? I can make it more advanced. I can add a damping, I can apply a damping matrix plus c times u dot. I can add 1 if I wanted to. I did not do that in this example. Okay? If you were to calculate, now everybody here knows what, I mean, you haven't memorized at this time, but you guys know for a linear element what this matrix looks like, don't you? EA over L, 1 minus 1, 1 minus 1 minus 1, 1. Everybody knows that from memory now. If you actually calculate it for this, for a linear element, what you get is rho AL over 6, 2, 1, 1, 2. Okay? That's what you get for mass matrix. Now I can calculate M and K bold for a quadratic element. For a quadratic element, here is how it looks. It looks a little more complicated. Rho AL over 30, and then this is how it looks. Okay? K is given by this, and you already saw this in a previous lecture when we talked about quadratic elements. Okay, quadratic elements. So now I want to ask the simple question. Okay, do I know M bold? Fully. I know rho of the material. I know the area. I know L. For linear and quadratic elements, for either case, I know M. Do I know M? Yes. Do I know K? Fully. I know K is EA over 3L. So I know the modulus, I know the area, I know the length. So then I know that. Do I know the distributed forces? Yeah, that's given to the problem. It's given to you. Okay? So with that, I think we're ready now to determine now what is the only unknown that I have here then in this equation. Sorry? What is the only unknown? The displacement as a function of time. That's the only thing that I don't know in this problem right now. Okay? In the previous problems that you worked on before, this mass matrix was not present because we're not looking at transient problems. So all you had was KU equals F, and this U was not a function of time. You just calculated U for the given force. That was it. Okay? But now, we're talking about dynamic problem where you apply a forcing function to the problem and the displacements can vary as a function of time. Okay, is that clear? Can you see the difference? Okay, so it's not much more complex. It's similar to what we've done before, but now we're adding the mass matrix. And things are now a function of time, U. Okay? All right, excellent. So, how do I solve this? How do I solve this? Okay? So, I'm going to try to cut to the chase. Normally you'll teach Euler. Remember last week we covered backward difference, forward difference, central difference, right? That works very well, actually, for problems where the derivative is respect to time, only one time derivative. If you remember, heat transfer and moisture diffusion problems have only one time derivative. This has an acceleration term now. So I'm going to cut to the chase and get as close as possible to what Abacus has in their code without getting into the minutia. You understand what I'm saying? So I'm going to cover the method that's the closest to what Abacus has. Okay? on how to solve this time domain problem. Okay. At this point in time, by the way, this is exactly will be covered like a numerical methods course, typically. But I'm going to teach you that because it's important part of this class. Okay. All right. Let me. People get really lost in the details, but if you follow me, I think you will understand how this method works. Okay. I'm going to do a Taylor series expansion. I'll explain it to you from scratch without even going through the papers. These papers derive it. Okay. I'll try to cut to the chase as much as I can. Will you agree that the Taylor series expansion of this displacement evaluated at t plus delta t is basically u at t plus u dot at t times delta t plus 1/2 delta t squared u double dot t? Isn't that Taylor series expansion? I mean, instead of u dot, you probably saw before derivative of u respect to t, or derivative of u double respect to t squared, right? But this is just Taylor series expansion. Does everybody agree with me on that? Yes. Excellent. Thank you for saying yes. And so now when I do an expansion on the velocity, let's do an expansion of velocity. I have t plus delta t. So then I have u dot at t plus delta t at the derivative of u with respect to time. That's acceleration, isn't it? Yes? Okay. Any questions on this? This is fundamental. If you don't understand this, you will not understand the rest. So any questions on this at this point in time? Okay, excellent. Now I'm going to make a modification to this. This is a Taylor series expansion, but I'll make a modification to this to try to derive a method called Newmark method. This is the backbone of what Abacus has in their code. Okay, and it's not that hard. Okay, it's basically a linear interpolation between the future and the present, and we only do that to the acceleration term. So let's see what we're going to do here. So I'll take this u double dot term. You see this u double dot term? I'll take this term, and I'm going to interpolate it between the future and the past. Okay, so if for example, if I put beta 2 equals 1, then I basically have this term is getting replaced by u double dot t plus delta t. So I'm getting a value here that goes into the future. You see what I'm saying? If I put beta equals 0, this term goes away. I have this term, so I get I recover back Taylor series expansion. Okay? So it's a trick so we can interpolate between the future and the present. That's what that beta 2 is doing right there. Okay? Any questions on that? That's the only modification we've done to Taylor series expansion. We've taken this term and replaced it by a linear interpolation of the acceleration term between the future and the present with a beta 2 that tells me what kind of ratio I want from the future, what kind of ratio I want from the past. Okay? Is that clear? We're basically trying to approximate the solution to the problem. Okay? So we're trying to approximate the solution of the acceleration just like we were doing with central difference, backward difference, and or forward difference. It's just a different way of doing it. Okay? We're just doing that to the acceleration term alone. Now, we can do now the same thing with the velocity. So the velocity term, which is the second row here, that second row, I'm going to take the acceleration again, and I'm going to do the same thing. But I'm going to do it with a different beta 1. Instead of beta 2, I'm going to use beta 1. Why? I want to have more flexibility. So maybe I want to use forward difference here, or backward difference here, or central difference here, but here I want to use a different kind of interpolation scheme for the acceleration term. But you can see here, again, I'm taking my u double dot, and I'm interpolating between the future and the past with this beta 1 term. This beta 1 and beta 2 are selected. It's selected by you. If I want to use a forward difference, explicit, fully explicit, then I'll set beta to 0. So I'll set beta to 0 and then I'll set beta 1, 0, and I'll recover basically Taylor series expansion here at the top. Okay. All right, you guys get the idea, right? So just like last week, we looked at the differential equation at time t plus delta t. Everybody agrees that this equation, we want this equation to be true. We want this to be true. Okay, I want this to be true. This equation here was true at time t. I want this equation here to be true at t plus delta t. I really want that. Okay, so what I'm going to do is very simple. Okay, and please don't get bogged down by the math. It's actually fairly easy in concept. Okay, again, Taylor series expansion on the displacements, Taylor series expansions on the velocities, and all I've done here is a modification to the acceleration term, so I can interpolate between the future and the past, and here the same way. Okay, and so what I'm going to do now, I know I want this to be true. So since I know that this is true, okay, I want this to be true. What I'll do for u t plus delta t, I'm going to substitute this expression, this long expression. I'm going to substitute that in there. And then for ft plus delta t, I'll leave it alone because I know the forces. The forces are inputs, so I know what the forces are going to look like as a function of time. So I'll leave that alone, okay? And so when I substitute that, look at what I got. I got a mu double dot t plus delta t plus k times u t plus delta t, which is all this, all that, okay? So that's plugged in there, okay? And then I have that equals to ft plus delta t. Now, I understand when somebody shows you an equation this long, it's very, very normal, not have seen it before, to get a little bit in shock. But there's no reason to be in shock. I'm just showing you the steps to get to this equation. That is the equation that's important now, because what I'm going to do now, I'm going to factor out, do you see a u double dot t plus delta t? And you see a u double dot t plus delta t here? I'm going to factor that out. And you can see that's k, bold k, multiplied by delta t squared 1/2 plus beta 2 u double dot t plus delta t. I'll factor that out so that I only have n plus 1/2 delta t squared beta 2k u acceleration term in the future. Okay? And now equal to the rest of it. So what I've done is brought the rest of it to the other side of the equation on the right-hand side. Okay? Okay, I'll let you stare at this, for a minute. You track? Again, what I've done is I have a u acceleration term in the future here, an acceleration term here in the future as well. So what I've done, I factored that out. And I have a k bold there now, 1/2 delta t squared beta 2. That's what I have there. And then on the right-hand side, what I have is the remaining terms, k times ut, k plus u dot t, delta t. All those terms are now on the right-hand side. Okay. Now let me ask you a question, because it's very easy to get stuck on this particular problem. I want to ask you one more time, very quickly. Is mass known? Is k bold known? Is beta 2 known? Now you may pause for a second, but you know that, because I'll tell you the integration scheme that you will be using. I'll tell you, okay, this is what we should be using. This value is known. That depends. If I make beta 2 equals 0, maybe I get backward difference. If I have beta 2 equals 1, maybe I get forward difference. That beta 2 will be known. Do I know the time step? Yeah, we'll make sure we have sufficiently small time step so it's unconditionally stable and it's accurate. So we'll try to get that to you. Okay, so this I don't know. I don't know what that is. I don't know acceleration in the future. Do I know k bold? I hopefully know the displacements right now. I hopefully know the velocities right now. I know the time step. I hopefully know the acceleration right now. I know delta t squared. I know beta 2 because beta 2 is the integration scheme that we're talking about. Do I know the forces in the future? I know them. So I know all this. I know all this. I know all of this. So then all I have to do is solve for u double dot in the future. You agree? Yeah? One more observation. If I know m bold and k bold, and delta t was constant, I just kept delta t constant over time as I marched the solution forward. You agree that I don't have to calculate, I only have to calculate this only once? And so I only have to invert this once? So that's one advantage of keeping delta t constant, is that you only have to calculate this once. But the minute that delta t changes over time, you have to keep calculating that, inverting that every single time. So that's a computational expense that you take. But if you don't change delta t, you don't have to invert this every time. So that's one advantage of what we're doing here. Now, this is very cool, guys, because if I know the acceleration right now, and I know the velocity right now, and I know the displacement right now, and I have the delta t that's going to march me forward in time, and I know the force in the future, then I know the acceleration that I'm going to have, the prediction for acceleration coming up. So, in a particular problem, if I know t at t equals 0, and I'm given initial velocity, initial displacements, but I'm not given initial accelerations, then this equation has to be true. Has to be true. Is this true at every time? It is true. So I know this guy, I know that guy. You can calculate accelerations from this equation. And now I have the initial conditions to my problem. Now I know the initial velocity. I know the initial displacements. I know the initial acceleration from the beginning of the problem. With these three, now at time equals t1, a little bit forward in time. So right now it's t equals 0. I want to look at t equals t1, just a little bit from now. I know that. I know that. I know that. I can calculate the acceleration just a little bit from now. So I know t equals 0 is now, and then t equals t1 is basically delta t, right? The change in time that I'm assuming. So with that information, I'm primed. If I have the accelerations in the future at t equals t1, with that information, I can plug that in here again into my formula for u, bold, that we had earlier. And if I know acceleration in the future, I plug it in here. I know the acceleration right now. I know the velocity right now. I know the displacement right now. I have the displacements that correspond to t equals t1. Not only that, if I have the acceleration, again, I have the velocity at t equals t1. You agree with what I've just said? Let's look at t equals t2, a little bit forward in time. Now I know, now t equals t1 became the present. You agree? Now I know what t equals t1 is now. I'm going to look at what happens at t equals t2, just a little bit from now. And at t equals t2 is basically t1 plus delta t, a little bit of change from now. And t1 is now, t2 is in the future. So everybody agrees right now that I know all these values. I just calculated them. Okay? I know all these values. I know ft2 in the future, t equals 2 in the future. I know the force in the future. Then I know all these parameters, so I know the acceleration, again, at t equals t2. Now if I have that, plug it back in here. I know the acceleration right now. I know the velocity right now. I know the displacement right now. I know the displacements in the future at t equals t2. And again, with the velocity the same way. I know the velocity at t equals t2, which now becomes the present. Now I have the accelerations, the velocities, the displacements. Okay? And now we repeat the process here again, back and forth. It's a recursive formula. So now I'm giving you the recipe for Newmark's beta method. It's called Newmark's beta method. And these are the parameters you can use for beta. So for beta 1 equals a half, beta 2 equals half. That's called the constant average acceleration method. This method is stable. Okay? It's stable It actually, so what I gave you actually is Newmark's beta method. Is the most general method that Newmark has. And then for different values of beta, you can specialize it for different methods. Okay? I don't want you to memorize any of this. That's not my goal here. My goal was to show you Newmark's beta method because it's the most general method. And then for these particular values of beta, you can actually get different techniques. So for the explicit scheme, we have beta 1 is 0, beta 2 is 0. Okay? Backward difference method, if you make beta 1 3/2 and beta 2 equals 2, you'll get the backward method. Central difference method is beta 1 equals 1/2, beta 2 equals 0. Okay? And some of them are conditionally stable, and some of them are stable to begin with. Okay? And we talked about that. Conditionally stable or means that I need to have specific restrictions on delta t for me to have a stable solution moving forward. Time march solution not to go unbounded. An oscillatory response that does not make any sense. Unphysical response. So the critical time step for stability can be found as follows. So if you, for this Newmark's beta method, if I have the stiffness matrix and I have a mass matrix, and I calculated the eigenvalues of this equation here, the maximum eigenvalue drives the critical time step for stability. Okay? So if I have the values of beta 1 and beta 2, my time step cannot be larger than whatever I get here, because if it's larger than whatever I get here, then I will have an issue with stability, and things will go unbounded. The solutions will become unbounded. Now, this technique that I just showed you is unconditionally stable if these parameters are true. Doesn't matter what you do, this is going to work. Meaning, it's going to be unconditionally stable. There's no conditions to it other than the values that I provide to beta. If they follow this, then I don't care about the time step. Now, if I take too large of a time step, the only error I can potentially get is an error on the solution because the delta t is too large. But if delta t is sufficiently small, you don't have to do this check because I'm telling you it's unconditionally stable. Okay, that's the question.
So how do we calculate lambda max? Because u is function of time.
No, this becomes an eigenvalue problem. Okay, so if you have k and m, you can determine the eigenvalue problem. You can calculate the eigenvalues to this right here. Okay. All right. So let's go to an example. I think an example works well, particularly when I do an example by hand and it matches abacus. Isn't that cool? I think it's a great thing to check out. And I had forgotten one little fact. Okay, and it drove me crazy. Because this is the first year I'm trying to actually cover dynamics in an introductory class like this. And I run abacus, and I get a different answer from what I got by hand. And I cannot determine why. It's kind of like what you guys are experimenting with problem 2. Except I'm the one teaching here, so I have to have material to present to you. So I have to figure out why this was not working. So we'll get to that. That's to build up the suspense. Okay, so let's consider 1D elastic bar. And what I'll do is 200 inches long, and the cross-section area is 1 inch. All the information is given here. Steel is about 30 MSI. The density is 0.29 pound per inch cube. I converted it to pound for second squared inch to the fourth, okay, to have everything in consistent units. It's fixed on the left. And on the right, we're subjecting this right end to an instant constant load on the right hand side of about 1,000 pounds. So I'm taking this right hand side and instantly loading it up. So that's what we're doing there. And we're saying that the bar has no deflection or velocity initially at time equals 0. So the question is, how does this structure respond? How does it, what happens to the structure? Okay, and it's not deflection equals PL over EA. Okay, we're not applying 1,000 pounds very slowly. Okay, if we're applying 1,000 pounds very slowly, then at the very end I can calculate the deflection, and it will be PL over EA. But in this case, I'm applying 1,000 pounds instantaneously. The structure is in rest. Instantaneously, I'm applying 1,000 pounds, constant over time. And I want to know how the structure responds. That's the question. So just for fun, we'll do two elements, element 1 and element 2. There's 3 nodes because it's a linear element. If it's quadratic element, you'll have 1, 2, 3, 4, 5 nodes. But these are linear elements. We'll have a linear element here, a linear element there. Okay? And I went in and got the mass and stiffness matrix. Mass and stiffness matrix for element 2. I did the assembly. Everybody knows how to do assembly here. Everybody knows the only new part could be this guy here, but I already told you, if you check it at home, you'll see that these are the mass matrices you get. So no problem there. I can assemble it, and basically all you get is a superposition of this over this. So you get 4 in the middle. And then here you superimpose that here. When you assemble it, you get 1 minus 1, 0, minus 1, 2, minus 1, 0, minus 1, 1. Okay? And then I have these forces here, okay, at the right-hand side. Okay, so getting closer to what we need to do. So this is assembly of the system, the assembly of the system. So what I've done here, initially the system is at rest. Initially the system is at rest. But also, I want to impose the essential boundary conditions. On the left-hand side of the bar, you agree that its clamp is fixed? So on the left-hand side, is there any displacements? Is there any velocities? Is there any accelerations then? No. So the first node, which corresponds to the left-hand side, the node on the left-hand side, that's clamp. That's not moving. So the acceleration is 0 at all times. Doesn't matter when. The displacement is 0 at all times. Okay? And if I had a damping matrix, if I had damping in this problem, then the velocity will be 0 initially too, and over time also. Is there any loads applied? Oh, because I have a displacement acceleration fixed equals 0, don't you agree that I have a reaction force Q1 that I don't know what it is? You agree? Excellent. Do I have any load applied in the middle node? Any load applied in the middle node? No? If you go back, the problem statement says only the load is applied here, not in the middle node. So I go back here, and that's 0. Hey, in the third node, which is the right-hand side, that is my load that varies as a function of time. I know that. In a normal problem, right? In a normal problem, I will tell you, hey, I apply 1,000 pounds. Slow. I didn't tell you slowly before because we're assuming static, right? But now I have to be careful. I have to tell you that it's instant. We got to do it instantly. Okay, so the first equation, I don't really care right now because if I multiply the second equation by the first row, this U1 double dot is not contributing in any way at all. So I can ignore the first equation, reduce the matrix into a 2 by 2. So it's just this corner here. And when I do that, I come up with this equation here. 2 equations, 2 unknowns. Okay? Simple so far? Yeah? Now I'll go ahead and impose, I will use Newmark beta method to solve for the deflections and accelerations as a function of time. That's my goal. Okay? Step 1. Step 1, I know the initial conditions. I know the velocity and the velocity and displacements are 0 at the beginning. I told you that. But because I applied the force instantly at the beginning, it's unclear what acceleration is at the beginning. So we need to go back to the equation, to this equation, to the equation that we just came up with here. Okay? And I'll plug in what U2 and U3 are. Those are 0. Okay? And I'll plug in what the force is 1,000 pounds. And from here, do you agree that I know everything now? I know everything. I know this. The only thing I don't know is accelerations. So I'll solve for the acceleration so I know the initial accelerations in the system. And when I do that, when I invert this matrix, mass matrix, and I multiply by all this, I get the initial acceleration. So I get an acceleration of 47,000 pounds to the right. And the middle node, I get an acceleration that goes to the other side, other way, of negative 11,742 inch second squared. Okay? Any question on what I did there? All I'm trying to do right now is to define the initial conditions of the problem. Because it turns out if you use a small time step and you start it with an acceleration of 0 at the beginning, and I just use a small time step, the very next time step, if it's small, it's going to give you this number anyway. But I'm trying to teach you how to do it correctly. So it's fundamentally correct at this point in time. Okay. Now I know the velocities, the displacements, and accelerations at time equals 0. But now I realize that these nodes, middle node and the right node, have an initial acceleration. Okay. And so given that information, all I have to do is to use Newmark's beta method, which is what I'll use. And I'm going to use a beta of a half and beta 2 equals half. That's because I like that method. That method, first of all, if we look back, is stable. And it actually is proven to work, so why not just use that one? I could have used all of them, solve the problem with different betas just for fun. But for the purposes of this for this class, I've chosen beta 1 equals beta 2 equals 1/2. I'm going to use a time step of 1 10 to the minus 5. So if time equals 0 now, I'm interested in what the solution is at time equals 1 times 10 to the minus 5. Just a little bit from now. I want to know what's the solution to the problem. There's a question.
Yeah. So in the proximate function, there are only beta 2 parameters there. But you are seeing the Newmark beta method, there are 2 parameters, beta 1, beta 2. And,
So Newmark beta method has a beta 1 and a beta 2.
yes, but in your approximate function, there are only beta 2 function. I'm
In-
not sure where.
Beta 1 is?
Yeah.
I'll show you where it is. Well, just for the video, the question is, this method has beta 1 and beta 2. So the beta 1 and beta 2, let me take you back. Beta 2 shows up in this equation, and then beta 1 shows up in this velocity equation. Okay. So remember when we talked about using Taylor series expansion? I talked about using Taylor series expansion, right? Remember this? So I said let's take the acceleration and interpolate the acceleration for the velocity term to be different in the way I interpolate that versus the first equation, which I'm interpolating with beta 2. So we're just independently interpolating the accelerations between the future and the present for both the velocity term and displacement term. Going back to the problem, there's another question.
Question about the acceleration sign, so when you say positive, positive is to the right or to the left?
Positive to the right. This acceleration is to the right. The middle node is experiencing acceleration to the left.
Forces towards the right?
Absolutely. The force is to the right. Hey, so what I can do now, I know K bold, I know all these values, I know delta T. Delta T is 1 times 10 5, right? Just that. I know the displacement at the beginning is 0. I told you that. Velocity is at the beginning is 0. That's why you see 0 there. You double that. I just calculated you double that to know what they are at the beginning, and that's what I plug in there. I'm using the constant acceleration method, so I put beta 2 equals 1/2. And when I work through this math, I get the accelerations of not too far away from what I got before, not too different. So it turns out if you had started with an acceleration of 0 here, you'll have gotten something close to that. Okay, but I'm showing you how to do it correctly from the get-go. Because if you got a bigger delta T, now that matters and it could be off. So we're just lucky that delta T is so small, it's just giving you an acceleration at time equals T equals 1 times 10 to the minus 5. Now I want to know what the displacement is. Remember, I don't know what the displacement is at this time, at 1 times 10 to the minus 5. I don't know what the displacement velocity is. I want to know that now. And so to calculate that, I just use the formulas. I know the accelerations at t equals 0. I know the acceleration. I just got that number. And I got that number. I got that number. I know the beta 2 and beta 1 is 1/2 for each of them. Then I know the velocity and displacements at t equals 1 times to the minus 5. And I gave you the calculations right here. Okay, I didn't give you the answer because I just created a code to do that. MATLAB will be even easier. I think I use Mathematica. Okay, very quick. Once I have the displacements at t equals 1 times to the minus 5, and I know the velocity at 1 times to the minus 5, I can now calculate the accelerations now at 2 times 10 to the minus 5. And my delta t is the same. My delta t is this minus that, so it's a delta t of 1 times to the minus 5. I'm keeping that the same, so I don't have to calculate this again. I'm going to just do this once and get over it. Okay? And then now, I just plug it in. I know the forces in the future. They're 1,000. I know the acceleration from the previous step. I know the velocity from here. I know the displacement from here. Let's plug it in and get the next accelerations at t equals t2. Okay? And that's what you will do in that step. Then, once you get the acceleration from this step, acceleration from this step, now I go and calculate the displacements and velocities at that time. And then, once I get this, I'll get the acceleration at t equals 3 times to the minus 5. And then I bore you from there. Because the steps repeat. Once I get that, I get the displacement velocities. Go back over and over here in this page. Keep going here. Okay? Do you guys follow the steps?
So you said the force is instantaneous. For how long is it applied?
In this problem, I applied it forever.
Oh.
Yeah. But you could have a problem where I applied it initially, and I drop it to 0. I could do that. We can do a lot of cool things now. You can model impact damage, or you can model different scenarios. Okay, so, all right, do you guys get the idea on what we're doing here? We could do a person on a diving board. They're standing there, so it's deflecting the board, right? That could be a good homework problem. The person is standing on the board, right? They jump, but they put an initial force, don't they? Initially, they kind of jump downwards a little bit, and then they jump up. So that's a cool problem because initially you have a deflection, right? Then they put an initial force, and then the board goes. So what the board goes, it just starts vibrating, right? That's a dynamic problem. It's not a static problem. Have you seen sometimes those diving boards go bananas? They actually accelerate more than what it should look like. Okay? Why? Because if the forcing function of the person, the frequency of that force from that person bending that board matches the frequency of that beam, the beam is going to accelerate even more. Okay? Hey, I did it in Mathematica because I thought it would be easy for me to do. I should have done it in MATLAB on second thought. But one reason I like Mathematica is because it's easy to display for me and to show. But if you're not used to it, it's fine. I'll show you. So I define the modulus, the length, the area, and density. Mathematica disagreed with me when I just put a single e because I guess it's protected for exponential or something. So I've made it EE. I chose the time integration for beta 1 to be 0.5, beta 2.5. I made the time increment to be 1 times 10 to the minus 5 because that was my example problem. I calculated mass, stiffness, matrices. You can see them here, rho AL. Do you recognize this? That's my 2 by 2. And my stiffness, my 2 by 2 for that. Now, I don't know if you remember, but we have to calculate this over and over and over. I have to calculate this over and over and over, remember? So I actually did it just once at the beginning. So I did it once at the beginning. M plus 1/2 delta t squared b 2 times k. I just did it one time, calculate the inverse at once, and call it m hat inverse. I just called it that. I said, okay, hey, the displacements, the acceleration is 0, velocity is 0. We know the acceleration is not 0. It was an initial value, but I wanted to show you that I get the same answer if I made the acceleration 0 for a small time step. And then I did a do loop here. It doesn't look pretty in Mathematica, but I just plugged it in, into the formulas I showed you. Those formulas, and in sequence I got W, the displacements and velocities. So in sequence I just got it, and I printed it and then imported the results into Excel. This is what I got for the end deflection. So the end deflection as a function of time got me this, and so that's sort of what I expected for the Newmark beta method. Then I was interested, what will Abacus give me? What will Abacus give me? That was a reality check. Okay, so this Abacus input file, not very different from what you've seen before. I used a truss element, but because truss elements have 2 degrees of freedom, I made sure that truss element didn't go flying vertically. So I fixed the degree of freedom going vertically so that it only moves axially, because we're looking at truss. I'm just looking at an axial bar. So I used 2 elements. The length is 200. I put a density of 0.073, modulus 36, Poisson ratio 0.33. Here, I set the left-hand side fixed, because it's clamped on the left-hand side, the node 1. I put the amplitude. I put the amplitude, and I call it name equals constant. So at time equals 0, I made 1,000. And time equals 0.1, I made 1,000. Now, you're asking me, did I make it forever? I guess I didn't, but since I stopped the solution way before that, it doesn't know any better. So that's my amplitude definition. Nothing is being used right now. This is not being used in any way right now at this point in time. That'll be used later. Okay. Then I say, hey, initial velocity. The initial velocity is 0, so no velocities. So I should create a set called all, which includes all these nodes. And all these nodes, I'm making them 0 velocity. So that's what that means. In degree of freedom 1 and 2, both degrees of freedom. Now I start with the dynamic procedure, where you see all the stars. Step, dynamic, initial equals no, so it's basically taking no accelerations. I start with a time increment of 1e minus 5, and I'm going to go for 0.015 seconds. And I'm just letting it stay at 1e minus 5. I don't want it to change, because otherwise, I want to compare apples to apples. There's a question.
What is I and C equal?
Oh, this is Abacus has a default of 100. So if you run the analysis in more than 100 time steps, it will stop. So I just overrode that, made a large number. So it was just to override it. But in a GUI, when Leonardo shows you on Friday, maybe you'll see how to do it there. I'm a little bit more still do things by hand. Okay, not familiar with the GUI as much. I'm running this for increments of 1e minus 5 until I reach 0.015 seconds. This is so it doesn't exceed. So if Abacus, if it converges very well, it'll increase the time step even further. So it'll increase the time step maybe to 2e minus 5, 3e minus 5. But because I want to compare it to what I did, apples to apples, and I wanted to compare it. If the solution doesn't converge very well, it will cut back the time step. I want to just maintain it at that number, 1e minus 5. This represents the maximum time increment, and this represents the minimum time increment. I'm forcing it to be the same as the initial time increment, delta t, the same delta t as I go forward. Boundary conditions is fixed on the left-hand side, 0, 0. All the nodes don't move vertically. You understand what I'm saying? I want to only solve the problem axially. So it's like an elastic bar. Then apply a concentrator load. This is where I'm actually calling out the amplitude. So I'll say, okay, node 3. Remember node 3 is where one I was applying the load on the right-hand side? Yeah? Degree of freedom 1 because I'm going axial. And then I have a 1.0 because I'm going to reference an amplitude constant with a name constant. You make up this name. You can call it your name. You know, amplitude equals Chris. Okay? Name equals Chris. I can do that. Then I'll have 3, 1 dot. And this 1 dot will get multiplied by this 1,000. Okay? And it's going to use this amplitude. This is basically saying 1,000 pounds at time equals 0, 1,000 pounds at 0.1 seconds. So it's keeping it constant. You define that. If I give you a sine curve, like a sine input, you will input that here. Okay, you will input that sine curve in there. And you will reference it here with 1.0. Okay? And then I just get the node output. I ask for velocities and accelerations and displacements. I ask for all of them. Any questions on these particular points that we made so far? That's just how to set it up by hand in Abacus. This just Abacus to save disk space is going to plot it every so often. I wanted to get the answers every single time I solved it. So at every single time increment, I wanted to know the answer. I wanted to get it so I could compare with what I got with Mathematica. You guys are ready to see what I got versus Abacus? Okay. Well, that was weird to me because initially when I did a sampling, I was comparing that to that number. At the same time, I was comparing that to that time, and that was like off by 50%, 40%. But in reality, it's not that off. It's kind of shifted a little bit there. And the dashed line is actually Mathematica, and the blue line is Abacus. And you can see it's not bad. It's not bad. I'm not going to disagree. Engineering-wise, looks great, but I was expecting exactly the same. Okay. And so my question was, well, maybe something else is going on. Maybe Abacus is using a different time integration scheme, which will be surprising to me because I thought it's using basically Newmark beta method, but maybe a little more advanced method, which is not really quite more advanced. It's basically the same thing. So let's explore that. Let's explore that. So Abacus uses something called the Hilbert-Hughes-Taylor method. It's called the HHT alpha method, which is basically Newmark beta method is a special case of HHT. Just a special case of that. Abacus uses HHT to basically improve the numerical dissipation for high frequency modes without degrading, the accuracy of the solution. But the main difference when I compare HHT to Newmark method is very simple. Is that this is Newmark method. Remember I said the solution has to be true at this point in time? Yeah? Well, with HHT, all they're saying is the stiffness is interpolated between the future and the present with this alpha. You see that? You see that? And then they're saying the force is interpolated between the future and the present with this alpha. So if I put alpha equals 0, you can see I get Newmark method. You see that? Yeah? HHT is unconditionally stable for these values, beta 1, beta 2, blah, blah, blah. You know what? I went in and put in HHT. I say, okay, what if I'm off? Let me run HHT with the values that Abacus has. And when I ran it, I still got the same answer that what I got. So then I said, okay, maybe Abacus is doing something else. And I remembered that maybe Abacus is doing the following. We'll talk about it coming forward. So now I want you to note something, that the mass matrix has to be inverted often, right? I have to invert that often. And to save computational time, what Abacus is doing is actually using something called lump mass matrix. They're constructing a lump mass matrix. Okay, and so there's several ways to lump in the masses to make them diagonal. All you're doing there is making the mass matrix diagonal by lumping all the off-diagonal terms into the diagonal term. I'll show you a couple of examples of how that works. One method is called the row sum method. You sum all the masses in one row and put them in diagonal term. Okay, and then the remaining mass terms that are off diagonal, you make them 0. This is called the row sum method, like I said. Lump mass formulation is computationally more efficient because when I invert the mass matrix, it's diagonal to begin with. So I can invert that very easily. And so let me show you how that works. So for example, remember this is a consistent, I'm going to call this consistent mass matrix from now on, okay? So the way that works is I add 2 plus 1 is 3. So I put 3 in here and 0 there. 1 plus 2 is 3. I put 3 here and 0 there. So I'm making that diagonals, adding all the row values, put them into the diagonal term, and the rest 0. Okay? So that's what I get. 3, 0, 0, 3. This makes sense. This makes sense because if I take rho AL over 6 times 3 is rho AL over 2. If I put rho AL over 6 here times 3, I get rho AL over 2. Well, rho AL over 2, rho AL over 2 is basically the mass of that element. But I'm putting half in one node, half in another node. Isn't the mass of that element rho AL? So I could put half on one node and call it rho AL over 2, and put the other half in the other node, rho AL over 2, is what I get. Okay? That's called row sum method. That's a method to lump the masses into the diagonal terms. And so now when I assemble it, I'm assembling these two guys, and what I get is basically 3, 6, 3. And you can see this is easily invertible. Right? You can invert this very quickly, by hand actually. Okay? Now, when I went in and ran Mathematica again, but with that mass matrix, I ran Mathematica again with that mass matrix. Look at that. It just matched. Okay? Right? So it gave me the same answer. So clearly, Abacus is mass lumping things to the diagonal terms. And that clearly also shows you that there's an error that you're incurring at the expense of computational time. Okay? Because when I did it, I was using a consistent mass matrix, which was fully populated. I had to invert that, right? And so here, when you lump it to the diagonal terms, there's less work in inverting that. Okay? Any questions in what I just discussed here? Okay. So then other ways to lump it, that's one method. Another method is called the Lobato rule, nodal integration. I will not cover this here. There's another rule called Hinton's rule. That rule is easy. That rule is basically delete all the off-diagonal terms. Just delete them. Don't worry about them. Make a 0, 0. Okay. Now, let me ask you this. Rho AL over 6 times 2, how much is that? 1/3? And then multiply this by, I get 1/3. So 1/3 plus 1/3 is 2/3. So my mass for the element is off. You see that? So what I'll do, I'll scale up by a factor alpha to bring it back to the total mass of the element. So I deleted the diagonal terms. I'm going to compensate for that with this alpha, and that alpha is 3 over 2 for this example. You can see very clearly that 3 over 2 times 1 over 6 times 2 gives me the exact same thing I got with this row sum method. Okay, so this is what Hinton's rule works out to be. I don't think it's necessary for me to cover Lobato rule because I don't think that's what Abacus is using, number one. And also there's many different ways to slice the cake, and I showed you 2 out of 3. All right, so okay, let's take a few minutes break before I hit Euler-Bernoulli beam. So come back about 5:18 and then we'll get started. All right, let's go and discuss now Euler-Bernoulli beam. So for Euler-Bernoulli beam, now I have a mass term right here times acceleration, but now the acceleration is also in a transverse direction. This is the strong form of the problem. It's mathematically true at every point in the domain. And then this equation can be used to calculate the transverse loads as a function of time, transverse deflections as a function of time. Here is a the residual function. I'll make it orthogonal to the space V of weight functions. And I'll integrate this over the domain, so that will form the weighted residual at this point in time. And then again, we'll now lower the continuity requirements because weak form Galerkin allows us to only satisfy the essential boundary conditions. And the approximation function that I select doesn't have to satisfy, doesn't have to be continuous up to fourth order differentiation. So because of that reason, we went in and integrated by parts. Again, I will do it only to the spatial domain, not for the time domain. Time domain will be discretized differently using a time integrator, while these ones will be integrated over the space. So we'll integrate this by parts, plug everything back in. I'll simplify the convention a little bit so that this is W double dot, a little bit easy to read. I'll use the double prime for x. So any derivatives with respect to x have primes. Any derivatives with respect to time have dots. And that's what we got. This, again, that's a weak form in a couple of steps. Okay? Maybe class number 3, when you saw this, you're in shock. But right now, you should be very, very familiar with this. Okay? If you're not, just come to me. Let's talk about it. Okay? So we've discovered that this is the essential boundary condition. We know that W is, anything specifying W is your essential boundary condition because V shows up here. And then there's a V prime here that tells us that W prime must be an essential boundary condition. This also tells us what variables must be continuous across element boundaries. Okay, I'll start introducing some terms like conforming element. A conforming element is one where the variable that we're, the essential boundary condition term, is continuous across element boundaries. We will then I've substituted this with Q's to have an equation like this. That's the weak form. Okay. All right. So these are the deflections and the rotations. Okay, for that beam. I'll give them names: V1, theta 1, V2, theta 2. V1 and theta 1 for node on the left. V2 and theta 2 for the node on the right. The approximation function I'll select will look like this: N1, N2, N3, N4. V1 theta 1, V2 theta 2. N times V or D gives me the approximation function, that multiplication. Where the N's are given by this shape function. These are the Hermitian cubic polynomials. We showed you already that these polynomials, when you plug this in, and I were to evaluate W at x equals 0, I get V1. If I plug in x equals L, I get V2. And if I take the derivative of W prime and I evaluate at x equals 0, I get theta 1, and so forth. You guys can check that. We've already gone through this exercise. Okay. Now I have an approximation function, a suitable approximation function, linearly independent, each of these basis functions. Complete set that satisfy the Kronecker delta property, the partition unity. Okay. Great functions. Now we have a Wx as a function of time also. In bold times d. I know I have to calculate this double derivative, so I'll do it here. Second derivative in bold with respect to x squared d bold, because d does not depend on x. So I get b bold d. B bold is this guy here. I also have to calculate the second derivative of w with respect to time. So I have n bold d double dot. For v, I have to make it n transpose, n bold transpose. And I also have to calculate v double prime, which will give me B bold transpose. I didn't do it, but you can imagine it right there. So the element formulation, simple. For V, I have N transpose, bold, double prime. That makes me B bold transpose. W double prime is B bold D. So that's B bold D right there. And so forth. You guys can see all the terms right there. looks very similar to the elastic bar. The only difference I will say, there's an EI here. In the elastic bar, there was an EA. But everything else looks very similar. Do you agree? Excellent. Now, I'll evaluate. Oh, one more thing. I brought the d bold outside of the integral. It's not a function of x. D double dot outside the integral is not a function of x. And again, the distributive force is this term right here. And these are the internal loads, moments and shear loads to that beam. Okay, excellent. Any questions? Yeah? Good? So let's move to the next step. Let's just calculate K, bold. Hopefully there's no negative sign errors. But this is what I did. So you have to calculate that. And then for n transpose n, you have to calculate this integral here. So let Mathematica do the magic. And you get K bold is this. I think that matches what's in the previous lectures for Euler-Bernoulli. M bold, this is the first time you see this. So that's rho AL over 420. And that's your mass matrix. I didn't evaluate this because this depends. If Q is constant, then you can evaluate it. If Q is something else, then it's something else. So I didn't want to evaluate that, but I want to show you how it looks. D bold is all a function of time. And then, in essence, I have M bold, D double dot plus K bold, D equals Q bold. Okay? Any questions on this? So, do I know M bold? Do I know K bold? I know Q bold. So then all I have to do is solve for D as a function of time. Any questions? Let's look at what the lumped mass matrix looks like for Euler-Bernoulli beam. A little bit different from elastic bar. So what is normally assumed for Euler-Bernoulli beam on a lumped mass system, on a lumped mass, is that the rotations don't contribute to the mass. So what they do, they make those terms zero. So they make this row 0, that row 0, that column 0, that column 0. And so that gives me this mass matrix. Okay, so that's what they do with a lumped mass system. The second thing they do, the row sum approach basically adds this row and puts them all in that location. Adds them all and put them in this location. So what is that? That's about 210. So I put 210 there and 210 here. Now rho AL over 420 times 210 is rho AL over 2 and half there. So I'm putting basically the mass on one node and the other half of the mass on the other node. That's what that method is doing. And then here at the bottom right is Hinton's rules method. You basically make this 0. And then you add the diagonal terms. What do I get there? 312. 312 over 420 doesn't give me the full mass of the system, so I have to correct it by a scaling factor alpha. When you do that, you get 420 over 312 times 420. 420 cancels. You can check it out. It's going to give you rho A. It's going to give you the same answer as this, basically. Half on one node, half the other node. Now, I thought Abacus was using this. I was wrong. Abacus was using the consistent mass matrix. It wasn't using a lumped. So I thought, oh, maybe since for an elastic bar, it used a lumped mass, maybe for Euler-Bernoulli beam, it'll use the lumped mass. Well, it used a consistent mass.
So how do you know everything?
Sorry?
Is it a keyboard or Abacus manual?
I actually didn't. I think it's there, but it didn't occur to me to check it until I ran it, thinking it's lump mass. Oh, let me match Abacus. Let me do a lump mass. Didn't match. Then said, but it's close. Okay, let me try consistent match. So, but I'm pretty sure it's consistent for that one. Okay, now, so let's do an example. We'll do 2 examples on this. It's not hard. It's the same process. All these things are tedious, I'll warn you. So the homework due next week is tedious. I won't lie to you. So if you wanted my Mathematica code, I'll give it to you. I don't care. All you have to do is change what the mass is, what the stiffness is, and then run the code. That will be Newmark's beta method, basically. I'm not trying to teach you how to use Newmark's method. That's not my goal. My goal was to teach you dynamics of FEA, finite elements dynamics, and I think I'm accomplishing that. If you want to do it yourself, do it yourself. I will not give it to you unless you ask me for the code, okay? So consider a clamped beam. It's clamped. The boundary conditions are as follows. Since it's clamped, the deflection and rotation is 0. At the right-hand side, I'm going to do something neat. On the right-hand side, I'm going to apply, at the very beginning, I'm going to apply an initial deflection of 0.2. So at time equals 0, I'm going to say the deflection is 0.2, and I'm going to let that go. Kind of like the person on the diving board example. The second thing I'm going to do, I'm going to take and say I have a distributed load that linearly increases with time. So I have 100 times t. So I have a linear load. So the load is uniform across the beam, but this linear load across the beam increases as a function of time linearly with this formula 100 times t. I also, to save me time, I just used one element to do this problem. Probably not the right thing to do, but enough for what I wanted to try for demonstration purposes. And then just trying to find out, how this system behaves over time. That was my goal. So the governing equations are this. You guys saw already this is a mass. That's a stiffness. If you check out the distributed load, uniform distributed load, you'll get this to be QL over 12, 6L, 6 minus L. You can go back to a previous lecture. For uniform load, that's what you get. So Q, I have 100 times T. Okay, 100 times T. So this is true at any point in time. I'm going to impose the natural and essential boundary conditions now. So when I do that, I already discussed that the first node, the left-hand side, is fixed. So this is 0. There's no acceleration there ever. The displacements are 0 and rotation is 0 at that end. We're not doing anything on that end. It's fixed. Because it's fixed, I have reaction forces, moment, and shear load. So I don't have to. I'm not looking to calculate this, although I could. Second thing is that I don't have any loading applied on the right-hand side. On the right-hand side, I have no loading applied. So Q3 and Q4, basically, I have no moments or transfer loads applied. So those are 0, in essence. So I impose the boundary conditions. And I'm basically left with a reduction in the equations of motions that look like this. Okay. I don't know why I have a Q3 there. Oh, I know why I have a Q3 there. I did apply a deflection, remember? I applied initial deflection at that node 3, node 2. So I should have a reaction force, some reaction force there because of that. But that's only true maybe at the beginning. I'm only doing that at the beginning. So it's tricky, it's a little bit tricky. So impose initial conditions of the problem at t equals 0. If I was you, I'll do this very systematically, just little by little, okay, to go through this. At t equals 0, that's my acceleration and acceleration terms. There's a displacement applied of 0.2 at that node, the right-hand side. I said that in the problem, there's no acceleration. Theta 2 is 0. Sorry, theta 2 is unknown. I don't know the rotation at that end. And that's equal to, at 100 times 0, there's no, this distributed load is not acting at the beginning. So t equals 0, that's 0. Q3, 0. So now I have two equations, two unknowns. I can solve for theta 2. So I can get the initial rotation at the beginning. Okay. You guys have a question on this? You follow it? Straightforward, right? Straightforward. Okay, so then I don't want to bore you with this, but the process is the same. Process is the same. Do I know the acceleration at the beginning? Yeah? Do I know the velocities at the beginning? It's 0. We said that. Do I know the deflections at the beginning? Yes, I do. I just calculated theta 2 and I calculated V2. V2 was given to me, was 0.2. Theta 2 came out to be 0.15. Okay, in the previous slide we calculated that. 0.015. 0.015 right there. And so now I'm ready. I can calculate acceleration in the next time increment. I know all these numbers. I know m bold, I know k bold. I'm going to use the constant acceleration method. So beta 1 and beta 2 is 1/2, 0.5. Keep it simple. Then once I know u double dot in the next time step, then I know substitute it here. Then I get deflections and velocities in the next time step. Repeat this for 1 through forever, as long as you want to go. And I call this M hat, M bold hat, just for my own sanity, to keep things look nice. Okay. Then I went to Mathematica, and I did it there, again, very quickly. Didn't take me time. Oh, here I calculated the initial conditions. So I got the theta of 0.015 right there. I just let Mathematica tell me that. Let's see what else I do here that's interesting. Oh, yeah, the initial deflections. 0.2 for V2, and then for theta 2, 0.015. You see it right there. And velocities and acceleration 0. Okay. Here I did a time incrementation of a dt of 0.001, just 0.001. I didn't do 1 times 10 to the minus 5. I did this about 100 times. We just ran it for 100 times. Basically running to 0.1 seconds. See what I got. Any questions? You follow it? Okay. Abacus implementation keys. I want to point some things I had to do. So here's my single element. Goes from 0 to 20. That's the length. B23 is my Euler-Bernoulli beam element. 2 nodes. Sorry, 2D space, cubic interpolation. My beam section is rectangular. Cross-sectional area is 1. Elastic. I took aluminum in this case, not steel. The density is in 0.0253. Fix the left-hand side. I put an amplitude here. Check it out. So the amplitude is increasing linearly. You see it starts at 0. Yeah? And it increases to a value of 0.1 at 10 seconds. Sorry. It increases the value of 10 at 0.1 seconds. That's a slope of basically 100. So that gives you Q equals 100 in essence. At this point, this is not being used until I tell it to use it. Look at this. Look at this. I started with a static step. I did a static step because I wanted to apply that deflection of 0.2 initially. I wanted to get that deflection in there initially. And then I told it, hey, don't have any accelerations on that. After you finish the static step, start the dynamic, but don't start things in motion just yet. Okay, so that's what the initial equals no doing. Fixed on the left-hand side, I have a distributed load that's uniform. You see this Py, that's distributed uniform load of 1.0 on element 1. I have only one element, and I have referenced increase here. So it's going to use that amplitude and apply it to that distributed load. You follow it? Py is my Q, basically, the distributed load, the transverse distributed load. Py is what Abacus tells you to name it. Like a distributed load in that direction is Py. Am I? Okay, Py. And then Px is axial. Okay? It's just, you can look at the Abacus manual and look at keyword manual. That's what I go to. Star deload, and I look it up. I'm not a GUI person because I learned Abacus when there was no GUI. Makes me, sounds like I'm old, but this is Abacus 1999. Okay, pretty back then. Yeah, back then we were just doing. I'll construct the. I'll tell you what I did back then. So I'll construct the mesh in Patran or some measure. I'll export it, and I'll just finish everything else by hand. I'll just kind of put the static step by hand, all those steps. It's actually benefited me a lot. Sometimes when I work with people, they use a GUI. It's like a black box, and I feel like I'm closer to the situation because I know what's going on with the input file. But maybe I'm wrong. Maybe my way is actually more prone to error. But I'm just used to doing it that way. Okay. Well, so now we can calculate the deflections, velocities, and accelerations, right? So when I do that, boom. That's when I said boom shakalaka, because look at this. Mathematica matches abacus. Look at that. It cannot be better. I mean, oh, by the way, does it make sense? Yeah. I'm increasing the distributed load, right? Am I increasing the distributed load linearly over time? So what's happening to the deflection? It's increasing. Why is it oscillating in the first place? Because I start with a deflection and I let it go, so it's going to start deflecting. Why is it deflecting the same amplitude the whole time? I didn't put any damping. Thank you very much. And I could have done that. I can add damping quite quickly, and I'll show you that on Thursday. Any questions on that? So, then I can take and I can run the same problem but with no distributed force, apply a deflection at the very beginning, and let it go to see what will happen. So I did that. Just same process, by the way. 0.0, I get the same rotation. By the way, one thing I want to point out is after the static step here, I checked it. I checked that my answer, 0.015, matched abacus. So abacus will give you the rotations and the deflections at the very end of that static step. And I was able to confirm it was 0.015. So that gave me confidence that what I have probably makes sense. All right, so ran it. Same process. You know, I won't bore you. Difference is I don't have a forcing function here. There's no distributed force. Just the deflection, initial deflection. So I ran that in abacus as well, by the way. I have a static step, dynamic step, but no distributed force. You see any distributed force there? No. No star deload. Everything else is the same. I ran the analysis. And again, abacus and Mathematica match quite well. And again, you expect this to oscillate back and forth. Makes perfect sense to me. Okay. It will be interesting for the elastic bar problem. I applied a instantaneous force. Remember that one, the elastic bar. If you calculate PL over EA, the deflection you should get at the end of that bar. PL over EA is the deflection you get at the bar from applying an axial force at the end of that bar. That's a closed solution for static problem. You will see that that number does not match the dynamic solution because we're doing it dynamically, right? There's an amplification factor for me applying things instantaneously. For this problem, we see that the deflections just go back and forth between minus 0.2 and 0.2 in essence. Very, very nice. Very close. Okay, how do I deal with a beam at some other orientation? It's not different from anything we've done before. The only difference is that your mass matrix is going to be transformed with this transpose. The transformation matrix transpose times the transformation matrix here. That's all you have to do. Everything else is the same process. From that point on, you know, you can just solve the equations of motions. So to summarize, and I'm not going to go through all of this. We already went through this derivation. The only thing I've done is add the mass term. Okay, but I have it here for completeness. Just to summarize, what I've shown you is how to run a dynamic simulation in abacus by hand. The GUI, you can actually in GUI do a lot more. You can create a mesh. You know, you can import the mesh. You can start from the CA CAD model. And then from there, you can just run a dynamic simulation, but I think you will have a better understanding what abacus is doing internally. You know, it's using the HHT alpha method. You know that abacus could lump the masses to the diagonal terms, like I learned. You know a little bit more about what's going on behind the scenes, because we also know how to do it by hand. That's one of the purposes of this class, is to teach you not just what abacus is doing, but what's going on with the processes. What methods are being used to solve the problem. So what we learned is that in a transient problem, We're discretizing the spatial domain using finite elements, and then we're integrating the equations of motion over time using the Newmark beta method on these problems. In the heat transfer problems, we can just use a forward, the backward, or the central difference method. And so, with that said, I think we're ready to now cover dynamics next Thursday for a special class of problems where we'll talk about modal dynamics. Modal dynamics. What modal dynamics is, you can imagine if I have 1,000,000 degrees of freedom problem, just imagine, I have 1,000,000 degrees of freedom, like an airplane or a launch vehicle, or a very large problem like an automotive part, you know. There's millions of degrees of freedom. And I'm integrating all those equations of motion over time, and they're coupled. You can imagine the difficulty in solving that in an efficient manner. Okay? If the problem is linear in nature, then using modal dynamics is very, very useful. Because what I can do is calculate, you know what mode shapes are? Anybody knows what mode shapes are? You can calculate the modes of the system, and I can just maybe calculate 15 modes of the system. Okay? And these 15 modes, if I take each mode and multiply by an amplification factor, a linear combination of these modes are added together, and I say that the response of the system depends on these 15 modes. And I don't care any of the other modes because they're not relevant. In a launch vehicle, for example, we'll calculate modes up to 70 hertz because everything above 70 hertz is not important. I don't expect my launch vehicle to deform jaggedy all the way from top to bottom. I expect it to be bending the first mode, the second mode, the third mode, torsion mode, maybe some other modes, but I don't expect a launch vehicle to have like 16 modes back, you know, from top to bottom, right? Only up to a certain amount of modes will become important to the response of the structure. In an airplane, you're not in a passenger airplane and suddenly you're walking down the hall and you see the whole airplane like bending like that. You know, hopefully that's not what's happening there, right? So we know that not all those modes are relevant. And so if I can describe the response, the dynamic response of the system in terms of, let's say, 10 modes, and it's basically a linear combination of these 10 modes, then I only have 10 degrees of freedom to describe a 1,000,000 degree of freedom structure. And I can get the stresses and the strains and the displacements for a problem that has been reduced in size from 1,000,000 degrees of freedom to maybe 10 degrees of freedom. And maybe I'll get very similar responses. This only, of course, works for linear systems. This is the most general method for nonlinear systems. So if I'm looking at impact dynamic problem where there's somebody dropped a tool on a composite wing, well, that's probably a little bit more, you know, you cannot just use linear dynamics there, but you could probably use linear dynamics to kind of characterize the general response of the structure. Okay, so we'll talk a little bit about that on Thursday. It's a huge topic. I mean, it can take many lectures to cover, but we will try to simplify it to a way where we can cover it here in 2 hours. And then next week, we'll be covering 2D and 3D finite elements. And from there on, perhaps we'll have time for buckling and some few topics of excitement, like fracture mechanics and buckling and nonlinear finite elements. Maybe we can cover that too. All right. Thank you very much for your attention.